Hi everyone. In the last class, we have discussed about orthogonal projections and mutually orthogonal projections. Today, we will discuss about invariant subspaces. Okay, so let us start with the definition of eigenvalue of a operator and eigenvector of an operator. Let T be a bounded linear operator defined on a Hilbert space H. A scalar lambda in C is called an eigenvalue of T if there exists x in H which is non-zero such that Tx equal to lambda x. This vector x is called the eigenvector corresponding to lambda. Again, an eigenvector corresponding to lambda. So if lambda is an eigenvalue, let us take M as null space of T minus lambda I. Lambda is an eigenvalue implies this space is non-zero. Now if you take x in M, then we have Tx equal to lambda x. So we know that x is in M. So this says that Tx is also in M. So whenever x is in M, Tx is in M. So if you restrict the operator to M, now this map from M into M. So such a space we call as an invariant subspace of T. Definition. A closed subspace M of H is said to be an invariant subspace for T in B of H if T of M is contained in M. If both M and M per orthogonal complement of M are invariant under T, then we can say that the space M is reducing subspace for T. If M per is also invariant under T, then we say that M reduces T. That means both M and M per are reducing. Okay, so let us look at examples of these spaces. Now we can ask the question, what is the advantage of having such space? For example, when we have eigenspace corresponding to lambda, here it is M. So T restricted to M is a map from M to M. And not only that, actually T restricted to M, here we can observe that is a scalar multiple of identity operator on that particular space. I suffix M is an identity operator on M. That means when you restrict the operator to a particular closed subspace, it is scalar times identity, which is a easy operator where we can get complete information about this operator. Okay. So let us see a few examples. If T is in B of H and lambda is an eigenvalue, then null space of T minus lambda I is an invariant subspace. If H is finite dimensional space, if dimension of H is finite, then we can show that T has an eigenvalue. Hence it has an invariant subspace. Okay. So let us take arbitrary bounded operator. Then we can conclude that null space of T is invariant under T. So we want to show that T restricted to M is contained in M. That means whenever X is in M, we want to show that Tx is also in M to show that M is an invariant subspace. So here when X is in null space of T, so Tx is 0, that is anyway element of M. M is NT here. So we can conclude that null space of T is an invariant subspace for T. We can show that range of T is an invariant subspace for T, but range of T need not be closed. So we can take the closure of range of T is invariant under T. We can show that the zero space and the full space H are invariant under T. So they are known as trivial invariant subspaces. But we expect an operator to have non-trivial invariant subspaces. Okay. So let us look at some more examples. Let us take the right shift operator on L2 defined by R of En as En plus 1 for all n in n, where En is a standard orthogonal basis for L2. So we define on the orthogonal basis in this way and extend the operator linearly to the full space. So in other words, we can say that R of x1, x2, x3 is 0, x1, x2, so on for every xn in L2. So we can take M to be span of E2, E3, E4, span closure we have to take. Then we can show that T of M is contained in span of E3, E4, and this is anyway subset of M. So we can conclude that M is an invariant subspace for R. So here this is R. Okay. Now if you look at M perp, that is span of E1, and if you look at R of M per that will shift one unit to the right. So this is mapped to span of A2. So which is not contained in M per, that is span E1. So we can say that therefore M is not reducing for R, or M does not reduce okay. So let us look at one more important example. Let us take L201 and look at the multiplication operator induced by 5. So let us take L infinity of 01 M5 at F, we are writing as 5F for every F in L201. So we know that it's a bounded linear operator and it's also normal. So let us take a subset of this, a closed subset. Define M suffix F as set of all F in L201 such that F of t is 0 for every t outside F. You can easily check that MF is invariant under M5. Now check whether this is reducing or not. Let us start with a non-separable Hilbert space. Let H be let us take X in H, which is non-zero. Then look at M as span X, Tx, T square X, so on, span closure. So we can show that, we can easily verify that M is a separable space and it is invariant under T, where T is a bounded operator. And let us take T be we can show that T of M is contained in M. So that is clear from the definition. When you apply T of M, you will get span closure of Tx, T square X, T cube X, so on. That is anyway contained in M. Now, since H is non-separable, so as H is non-separable and M is separable, M cannot be equal to H and M cannot be 0 also. So M is a non-trivial invariant subspace for T. Therefore, M is a invariant subspace. So we have shown that given any bounded linear operator on a Hilbert space H, which is of infinite dimensional, because we are assuming that H is non-separable, so we can show that M is defined in this way, is an invariant subspace which is non-trivial. Now the question arises, when does a given bounded operator have an invariant subspace? Let H be a separable Hilbert space and T is a bounded linear operator on H, which is not scalar multiple of identity operator, because for an identity operator every closed subspace is invariant under that identity operator. So if you take scalar times identity also, it will have plenty of invariant subspace. Is not a scalar multiple of does T. When does T have an invariant subspace? Non-trivial invariant subspace. So this is one of the open problems in operator theory, well known as the invariant subspace problem. So for several cases this problem is solved. For example, if T is a compact operator, we will be discussing about compact operators at a later stage. So known cases. Then T has an invariant subspace. Non-trivial. If H is finite dimensional, we have seen that dimension of H is finite, then the invariant subspace exists for T. T has an invariant subspace. So there is a famous result by N-flow, which is that there exists a Banach space X and T in B of H, which is not scalar multiple of identity. Such that T has no invariant subspace. Here non-trivial, because T can have always trivial invariant subspaces 0 and H. By the spectral theorem, we can say that every normal operator on Hilbert space also has invariant subspace. This will be proving at a later stage. And there is very well known theorem by Lomonosov. It says that if T is an operator which commutes with a compact operator, then T has an invariant subspace. And Tk equal to Kt, where K is a compact operator, then T has a non-trivial invariant subspace. Okay, so these are some of the known results related to invariant subspace, but still the problem is open. Okay, so the result which was proved by Lomonosov is more powerful than the invariant subspace, because it is saying the existence of invariant subspace for an operator which commutes with a given compact operator. So such a space we call as hyperinvariant subspace. Okay, so let us look at what is the advantage of having such spaces. So before discussing those things, let us look at some important results. Let T be a bounded linear operator on H, then the following are equivalent. M is invariant under T. Here M is a closed subspace. That is equivalent to the fact that T star of M perp is invariant under T star of M perp is contained in M perp. Let us take, so let us prove 1 implies 2. Assume that M is invariant under T. We want to show that M perp is invariant under T star. So let us take Y is in M perp. We want to show that T star Y is in M perp. So for that, let us take X is in M. Then we can say that T star of Y inner product with X is nothing but inner product Y with Tx. Now Tx is in M because M is invariant under T. So we can say that this is 0 because Y is coming from M perp and this is coming from M. So because of this reason it is 0. So from this we can conclude that therefore T star of Y is in M perp. On the other hand, 2 implies 1 is trivial again, because T star of M perp is contained in M perp implies T double star of M perp is contained in M perp. But we know that T star of T double star is T and N double perp is closure of M, but M is closed here. So T of M is contained in M. So here M is a closed subspace. A closed subspace. Then the following are equivalent. Okay, so this is a characterization of invariant subspaces. Let us look at some more characterizations. Let M be a closed subspace of H. And T be a bounded operator. So let us write P to be the orthogonal projection onto M. Its orthogonal projection whose range is M. Then the following are equivalent. M is invariant under T. If and only if PTP is TP. So we can express invariant of subspace in terms of orthogonal projections. So let us look at 1 implies 2. So let us take X is in H. Then we know that Px is in M. So hence we can say that if you look at PTPX, this is PTX because Px is, sorry, this is so PTPX, Px is in M. Now M is invariant under T, so that means Px is in M and TPX is also in M. So since P is an orthogonal projection, so this part is in M, hence we can get this as TPX. So PTP we have shown to be TPX. On the other hand, let us look at proof of 2 implies 1. So assume that PTP equal to TP. So let us take X is in M. Then we want to show that TX is in M. Look at TPX. So that is nothing but TX. So now TPX is nothing but PTPX. So this is in range of P, that is in M. So we have shown that whenever X is in M, Tx is also in M. So this completes the proof of 2 implies 1. Now as a corollary, you can prove the following. Let T be a bounded linear operator and M be closed. A closed subspace of H, and P is the orthogonal projection onto M. Then we can conclude that M reduces T if and only if Tp equal to P. P and T commute. Okay, let us look at the proof. M reduces T implies Tm is contained in M and T of M per is contained in M per. So this is again Tm is contained in M, and by the earlier result Tm per is contained in M per and only T star M is contained in M. So this we can say that T star of M is contained in M. That means M is invariant on both T and T star. By the earlier characterization we can say that PTP equal to TP and PT star P equal to T star P. So this implies PT star P is T star P. So this implies PTP equal to TP, and take the adjoint both sides, you will get PTP is PT. So therefore PT equal to TP because P star is P. Now let us look at what is the advantage of having such invariant subspaces. Let M be a closed subspace of H. And T is a bounded operator on H. Now H can be written as orthogonal direct sum of M with its orthogonal complement. Now T we can decompose with respect to M and M per. Hence we can see T can be written as 2 by 2 operator matrix. This is T11, T12, T21, T22. So this is M, M per, M, M per. That means T11 is a map from M into M, T12 is a map from M per into M, T21 is a map from M to M per, and T22 is a map from M per into M per. Now let P is an orthogonal projection onto M. Now with respect to M and M per, we can write down the operator matrix of P also. So P can be written as here M, M per. Now range of P is M. So on range of P, P is an identity operator. So this is an identity operator on M. And now P restricted to M perp is 0. So this 0 map from M perp into M. Now this is also 0 because P of M is contained in M. So it cannot map any element into M perp. Now this part is M perp into M perp. So M perp is a kernel for M, a kernel for P. So this is also 0. So note that this is 0 map from M perp into M, and this is a 0 map from M into M perp. So this is M perp, this is M. Okay. Now we know that M is invariant under T if and only PTP equal to TP. So if you look at this 2 by 2 operator matrix and compute this PTP and TP and equate, so we will get 0, 0, 0, T11, T12, T21, T22 into IM 0, 0, 0. This we can get as TP. This is T1, T12, T21, T22. This is IM 0, 0, 0. So this implies this is T11, T12, 0, 0. This is IM. This is nothing but T11 0, T21 and 0. So this implies that T11 0 0 0 equals to T11 0, T21 0. So from this we can say that T21 is 0. Now we can actually show that whenever T21 is 0, we can compute all these steps and conclude that PTP equal to T2. That means M is invariant. So whenever M is invariant, it is necessary and sufficient that T21 part, this part is 0. And we can show that when M perp is invariant under T, then we can show that this part is 0. So we can easily, using the same step, whatever we have done so far, so we can easily show that M reduces T if and only if T12 is 0 and T21 is 0. As I mentioned earlier, so there is a difference between this 0 operator and this 0 operator. The first one is a map from M perp into M, and second is a map from M into M perp. So though they are 0 operators, their domains and codomains are different. So in the case that when M is reducing space, this implies T can be written as T11 0 0 T2. This is M, M perp, M, M perp. So we can get a diagonal operator matrix, and if you can analyze both T11, T22, you can get information about T. So we can easily check the following. Null space of T is null space of T1 direct sum with null space of T2. Similarly, range of T is range of T11 direct sum range of T2, and we can show that T is 1 to 1, also on to if and only if T11 and T22 are 1 to 1, on to. And we can discuss many more such properties. That means we can look at the operator on a reducing subspace, and if you adjoin all such operators to get the information about T. Okay, so these are a few important properties of reducing subspaces. So one important application we will be seeing at a later stage, that how to decompose a given Hilbert space as direct sum of reducing subspaces, and how to write down the operator as direct sum of identity operators on the particular reducing subspace. So those properties we will be looking at a later stage. Thank you.